Hi everyone. So I think we'll wait for some seconds and until people come, and then we'll start our presentation. Okay, so let's start. Hi everyone. So thank you for joining us today, and I hope that you and your families are doing well and healthy. So I'm Rihab Gorsane. I'm from Tunisia, and I'm Google developer expert in machine learning, and I work as research engineer at Ansadib. So welcome to Google Digital Mina Days. So it's basically each week from Sunday to Thursday, you've got a lot of sessions about Google products, workshop and talks starting from 7 to 11 p.m. Dubai time. So please, for those who are new, please check out those links. So here you can find the link to the Google Mina website, when you can see the whole agenda that gets updated every day. Also, you have a link to the YouTube channel, as well as a link to the Quick Lab code that you will be having access to. So you will be having access to a lot of quests and tutorials in different fields. And there's also the feedback form link. This is important for us that you fill it when you attend the session, because hearing about your feedback allows us to improve our content, as well as you can propose topics that you would like us to discuss about in the upcoming session. So once you fill the feedback form, you will have an attendance certificate. And also, there's a link to the Mina Google Days challenge that you can participate in. So basically, now we are in week 4, and today today is the last session for today, which is about general advices about reinforcement learning. So what we will do today, we'll start by giving an overview on the reinforcement learning field, try to discuss what's the difference between sequential decision making and supervised learning, and then we'll discuss about the tips and tricks while trying to work on reinforcement learning project. I've tried to gather the insights from online blogs, talks, and also my own experience, and I come up with these questions that you can find here that you may have asked yourselves before, or you may encounter while working on a reinforcement learning project. And we'll try to answer that. After that, we'll move to conclusion, and eventually, if you have any question, you can write it on the dialogue chat. I will try to answer it as much as I can. So for that, and before we dive into the details of reinforcement learning, I just want to point out the difference between supervised learning and sequential decision making. So supervised learning is probably the first thing that we have learned in machine learning. We have so basically we have a set of training data where each point is IID sampled. So what I mean by IID is that identically and independently distributed from an unknown distribution, and we fit that that point to some function approximator. And for example, if we consider that we are training on images, so after doing the training, afterward we give our trained model the new test image, and we just make prediction. And here, the whole process is considered as passive, in a sense that you make a prediction on a test image. It's not going to affect the future image that you're going to see, because here we are assuming that every data point is IID sampled from an unknown distribution, and thus your prediction is not going to affect the data distribution. But this concept is fundamentally different in sequential decision making, where everything is active. For example, the sequence of images that you see here are highly correlated to the action that you have taken. So basically, if you have applied bad actions, your future state space will be basically looks like this one, as you can see. You can see here, if you have applied bad actions, your state will be oftenly having the agent falling into the river, which is considered as bad action. And if you would like to go to state where you want to collect a larger reward, we mean, like here, you get a bonus when entering a door. You need to learn to make those decisions sequentially to get to those state space. In short, your decision highly affects the data distribution that you're going to see, and and learning sequential decision making is often captured by two main components. So basically, you have an agent and an environment. These two components are interacting with each other. So the environment first gives the agent a state, or what we call also an observation, and the agent in turn has to take an action, and the environment will give back a reward, telling the agent how bad or how good the action it took was. So as well as the next observation, or what we call also the next state. This RL loop keeps going on and on until the environment gives back a terminal state and ends the episode. So the environment that you are discussing about is a representation of the world. So it could be a classic problem like the cart pole problem, where the objective is to balance a pole on the top of a movable cart, as you can see here. So your state here will be the current description of the system. It could be the angle, the angular speed, the position, the horizontal velocity of your cart, and the action here that you could take are the horizontal forces to move the cart around to balance the pole on the top of it. And the reward here that you're getting from this environment is one, at each time step the pole is upright, and basically you would like to keep the pole balanced as long as you can to get to your goal. So the environment could be something simple like this, or it could be also something more and more complex and represent a game. For example, such as Go, which is considered as a great achievement in the reinforcement learning world when DeepMind's AlphaGo beat professional player Lisa Dole in 2016. So the objective here, of course, is to win the game. However, the state is very big. So the state is the position of all the pieces on the board, and your action space, in fact, is very big because you've got to decide where to put the next piece down on the board, and your reward is 1 if you win at the end of the game, or 0 otherwise. So this is basically the reinforcement learning loop that is considered in different environments. And now that we discussed about this loop, we having the environment providing states and the agent taking actions, how can we mathematically formalize this reinforcement learning problem? So we have a Markov decision process. It is the mathematical formulation of the reinforcement learning problem. So an MDP satisfies the Markov property, which tells us that the current state completely characterizes the state of the world. So what exists in the current state, it has the whole information about the characteristic of the environment. You will not need to know about what were your past states. And also, The MDP is defined by tuple objects consisting of, for example, first S, which is a set of finite state, finite set of states, which is also the observation that I was discussing about. A, which is the finite set of action that you might have taken, and P, which is the transition probability distribution over your next state that you're going to transition to, given the state and action pair that you have taken. There's also R, which is the reward function, which is the transition probability of the given reward, given the state and the action that you took at that state. And finally, there is gamma, which is considered as the discount factor, which basically says how much we value what comes up soon over versus what comes up later on. So, and in the reinforcement learning framework, our objective here is to find the optimal policy pi star, which maximize our cumulative discounted reward, and which is the sum of our future rewards, which can be discounted by the discount factor. And what we mean by policy here, the policy is the mapping from states S to action A. It basically specifies what action to take in each state. So our goal is that we can define this policy to be optimal at the end of the training. So reinforcement learning has seen a lot of progress through the years. So we have ranging from DeepQ network in 2015 on Atari games, then AlphaGo on Go, and generalizing AlphaGo through AlphaZero on chess, shogi, and Go. Then we have Dota 2 in 2018, and Go Explore in 2019 on Montezuma Revenge, which is considered as hard exploration task. And then there's DeepMind on DeepMind work AlphaStar on StarCraft. And the list is keeps on growing. So, and of course, there's a lot of theory and algorithm that led to those achievements. Here we cover a little bit the landscape of algorithm in modern reinforcement learning. And for the purpose of this presentation, we will not go into the details of this algorithm, but it's important for you to know them and understand how they work. So one of the first branching factor in reinforcement learning algorithm is whether you have model-free reinforcement learning or model-based reinforcement learning. And what we mean by model-free and model-based, when you have when you would like to model the environment, we mean that you have a function that predicts state transitions and rewards. And the model-free that you will not predict the state and the transitions. And if you, for example, look at the model-free reinforcement learning, we can distinguish between two main categories. There's the policy optimization and also the Q-learning strategies. So in the policy optimizations, you have to optimize the policy directly. So you are optimizing it directly as we want it to be. And in the Q-learning, this is being done indirectly through some estimation equation. And you can find a variety of algorithms that you can find in each category, and also a combination of the both words of policy optimization and Q-learning strategy does exist. So basically, now that we have discussed about what reinforcement learning is, let's get to the serious question, which is how can I get started? So, like any other subject, if you would like to work in reinforcement learning, you should first read about it. So, and you would, and basically, you would be asking yourself, what are the materials that I should be tackling or I should read. So here I put some of the ideas that I totally recommend, and they are very known in the literature. So there's the reinforcement learning book by Richard Saturn and Andrew Barto, which is considered as the best book when you can find the theoretical details, and especially for people that would like to go into reinforcement learning research. So it's tough, but it's worth investing time on it. So there's also some teaching materials that you can find online, provided by David Silver, including video lectures, which is a great introductory course. There's also some technical tutorials on reinforcement learning by Peter Ebil and John Schulman. Here I provided the links that you can have access to afterward. And there's also another book that I totally recommend, which is Reinforcement Learning Hands-On. It's a book when you can find the theory and practice going in one hand. So you have the book and you have all the tutorials on GitHub that you can have access to. And for people that would like to join online courses, there's a lot of courses on Coursera and also on Udacity. You can check the Deep Reinforcement Learning Nano degree on Udacity. It's super interesting and gives an overview on the reinforcement learning field. And also you can check out blogs and talks online. I recommend the Andrew Kabathi Deep Reinforcement Learning Pong from Pixel, which is a great introduction to build motivation intuition about reinforcement learning. And there's also John Schulman talk about nuts and bolts of GPRL, which has a lot of tips about practical issues that you may run into while building reinforcement learning projects. So let's take, for example, let's take, for example, the use case when a person has already read about reinforcement learning, understands the theory behind it, and has a new task that could be solved with reinforcement learning. The question now is how to frame this new task. And the answer to that is that, of course, here, the first thing is that you should follow the MDP formalism. Remember the actions, states, transition, and reward that we just have discussed about? Mostly at the beginning, when you are building your first version of the environment, it's unclear for you to which state features to use, or which reward function to choose. So the first advice is that you start with a simplified version of your task until you see signs of life. So try to make it simple. Simplify your feature space, and once it starts working, make the task harder and harder until you solve the full task. Also about the reward function, which tells you how bad or how good your actions was. So try to simplify it, formulate it in a way that it can give you fast feedback to know whether you're doing the right thing or not. And once this new task is well formulated, you have to learn how to create a custom environment. So, and here we come to the OpenAI Gym toolkit. So, what is it, OpenAI Gym? So the OpenAI Gym is an open source library that does not only give you access to standardized set of environments that ranges from classic control, as you can see here, Atari, also 2D and 3D robots and algorithmic environments, but also it allows you the possibility to build gym-like custom environments and interact with them by just following the gym interface. So what you have to do is first to define your action space, what type of actions you can take. Also, you have to take define your observation space, and here you've got a lot of functions to implement, such as you can see here. These are the most important functions that you should have. First, the initialization of your environment. There's also the environment step function, which take the action that your agent has chosen and gives you back the reward, the next observation. and an indication if you are in terminal state or not, and some additional information about the environment. Another information, which is another essential method is the reset function, which is allows you to reset your environment at the end of the episode. There's also the close function if you're dealing with some simulator that are for example, like Atari should at the end of the game close the simulator, and also there's the rendering methods, which allows you to visualize your environment while doing the simulation. So while implementing your environment, try. For example, now I will try to delve deeper into what are the things that you should consider when you implement your environment. So while implementing your environment, try to look at the state features and that you have considered, and make sure that you didn't remove any necessary details about the environment in the pre-processing, or whether how you deal with them. You should always normalize the input you give to the agent and adopt the common processing technique that exists in the literature on other environment. For example, if you're dealing with Atari games, I'm giving the example of Ataris. So downsampling the frame screen, grayscaling it, and stacking 4 consecutive frames has been shown to provide better results than those done without using these pre-processing techniques. For example, for your action space, if your action space is continuous, that means that you're not taking discrete action. For example, you're not taking an action to move right or up, but you're taking the action to go with a certain speed with a value that is continuous. So if it's the case, normalize your action space and make it symmetric. So a good practice here is to rescale your actions to lie in -1 and 1 interval, because most of reinforcement learning algorithms rely on a Gaussian distribution initially, centered at 0 with standard deviation 1 for continuous action. So if you forget to normalize your action space when using a custom environment, this can highly harm the learning and be difficult to debug. Another point is about your reward function. When you implement it, try to use shaped reward, so you can get gradual feedback and let your agent know it's getting better, or it's getting closer to the final goal. So shaped reward is in contrast to sparse rewards, which gives the reward at the terminal state and no reward elsewhere. So shaped reward has advantages, as it's often much easier to learn because they provide positive feedback, even when the policy hasn't figured out a way to provide the full solution, but it has performed some good actions. Okay, let's suppose that you have taken in consideration all the implementation details that I was discussing about, and you have your first version of your environment ready, and you would like to start experimenting. So consider first debugging with random action. Check that your environment is properly working, and whether your environment it follows the GEM interface and the API is working properly. Once you validate this, try to visualize those actions, this random policy on your environment. So if your random policy does on occasion the right thing that you expect it to do, then there's a high chance that your reinforcement learning agent will do the right thing. But if your random agent never does the right thing, the reinforcement learning will likely also not. So now we come to the famous question, which is about which algorithm should I use for my custom environment. And basically, there's no by-the-book rule that tells you which algorithm you should work on using your new environment or your new task. but there's some hints that could help you out. First of all, you should really know your task and understand its needs. So, one of the first questions that you may have asked yourself is, uh, what is um, what is your action space? So, is it discrete, such as taking left, right, up, and down action in a grid world environment, or is it continuous, such as going to a certain speed, or even is it hybrid, such as going up with a certain speed? So some algorithms are only tailored for one or the other. For example, DeepQ network only supports discrete actions. First versions of soft actor critic model, SAC, were restricted to contain continuous domains, and now it does include both. And there's also hybrid PPO, for example, which is used for both together, I mean for hybrid action space. Okay, so if your reinforcement learning algorithm is a component in a larger system, so don't try and implement the reinforcement learning yourself. I mean, it's a fun challenge, true, but you will learn a lot, and you will learn a lot. But reinforcement learning is unstable enough that you will never be sure whether your system doesn't work because of a bug in your reinforcement learning implementation or of a bug in your larger system. Therefore, the first thing that you should do once you have your environment ready is that you try out baselines. And what I mean by baselines, the algorithm that I just mentioned before in the taxonomy of reinforcement learning algorithms. So, and of course, don't expect them to work with default parameters. So, reinforcement learning, good results are generally dependent on finding appropriate hyperparameters. So in short, before doing anything for your new custom environment, see how easily an agent can be trained on your environment with a baseline algorithm. So now that you have your environment, your set of baselines ready, you chose the baseline that you'd like to experiment with, and you'll start experimenting, and you will try to draw your own conclusion. So the first thing that you should probably do is that, especially if you are working in a team project, you should ensure that you have an automated pipeline for experimentation. So that allows every developer in the team to have an access to a battery of benchmarks and checkpoints available to compare the performance of each run. So, and if you have enough budget, consider also using cloud computing platforms. The second advice is that you should try to collect metrics that maximize the amount of evidence you gather on each run for your specific task. I think it might also be worth spending time and good chunk of time, at the start of the project, brainstorming and researching which metrics might be important for diagnosing your potential problem. The third point is that you should continually benchmark your code. So I tried to summarize it in three aspects. First, you should consider using random seeds. So reinforcement learning can be so unstable that you need to repeat every run multiple times and with different seeds to be more confident about the performance. Also, you should also consider when you've got a lot of feature in your state space, you should consider feature ablation. So basically, what you will be doing is that you remove and add one feature at a time and see if it has a large effect on the performance. And this way, you'll know whether to keep it or not. And the third aspect is that considering using different reward design. You should experiment with different reward design because finding the best reward function could be quite tricky at the beginning. So the fourth point is that you should be able to track your experiment, compare the performance, and draw conclusion. That's really important. And here, I think the main takeaway is that you should consider switching from experimenting a lot and thinking a little to experimenting a little and thinking a lot. Because after each experiment, you should commit yourself always to investigate whenever you notice a small confusion, because paying attention to the small details in your when you are experimenting could save you a lot of time and a large amount of time, because otherwise you'll end up spending time debugging, which is very bad. So the next question, let's say you already prepared your experimentation pipeline, and how do you really diagnose your reinforcement learning agent behavior? So, and to be able to diagnose your reinforcement learning agent behavior, you should establish sanity checks. This could be much easier if you see all your metrics in one place. TensorBoard allows that. So, for example, let's start by the main point that you should consider. For example, if you run some experiments and at each time you take a hyperparameter in a hyperparameter and you change its value, and you see that your RL agent is very sensitive to that change. This is considered as a bad sign. That means that your agent is not robust enough, and you should find ways to fix that. Also, when you have got a TensorBoard, you've got a lot of plots, and you will try to look at those plots and try to draw conclusion whether you're doing the right thing or not. So I try to sum up some of the plots that you may be looking at. For example, there's the episode return. What we mean by the episode return is the cumulative reward that you've got through the episode after playing some number of steps. So when you look at the episode return, try just to not only look at the mean value, but also look at the mean, the minimum, the maximum, and the standard deviation. These are important. And normally, you should see that your reward is increasing over time. And also try to have a look at the maximum return to see if your policy is ever doing the right thing according to the maximum return that you give in your environment, or it's really stuck. So if it doesn't get to that value, that means that something not working really as expected. And also, you can have a look at the episode length, and which is important, and sometimes it can be more informative than the episode return. Because, for example, if we take the example when you look at the episode return, you never see yourself win, but the episode length would tell you if you're losing slower. So you might see an episode length improvement, but you see no improvement in the return. Now we move to other health indicators, and we consider that health indicators differ from one class of algorithm to another. And here there's, for example, for model-free reinforcement learning, we distinguish policy gradients and Q-learning. Sorry. Okay, so how should I diagnose? One of the questions should be, how should I diagnose my reinforcement learning agent behavior when I'm using policy gradients? And here, to be able to properly diagnose your reinforcement learning agent behavior, you should have, as I said, the metrics that you should consider. And for policy gradient methods, policy entropy is in particular a good indicator of whether your training is going well or not. And here, please note that the entropy the entropy is a measure of uncertainty. So, being applied to the agent policy that's being trained, the entropy shows how much the agent is uncertain about which action to take. So, if the entropy is going too fast, that means that the policy is becoming deterministic and there's no longer exploration. And at the beginning, we would like that our agent explores random actions until it finds the optimal actions for its task. And if it's not going down, that means that it's a bad policy and it's taking random actions, which is not good also. So here you can see that here the third curve here represents a healthy entropy that starts here, for example, with random actions, and then it starts moving towards optimal actions. As you can see, the entropy is decreasing. That means that it's getting to the right path. Okay, so another metric that you should consider in your plots is the policy loss. So the policy loss, it should be decreasing during the successful training. That sorry, the policy loss should be decreasing over time, and to be able to prevent it from getting stuck in local optimum and alleviate it, we can use the entropy term and the KL divergence. So here, I just would like you to know that I will not go into the details of these features, but it's important to know their importance in terms of plots. So the policy loss should be decreasing during a successful training, and to prevent it from getting stuck in local optimum, we alleviate it using the entropy term that we just discussed about, which is measure about this uncertainty for the agent of taking an action. And also there is the callback labor divergence, because in the policy gradient, you're updating the policy with respect to the action that you just took, bad actions and good actions. And there's the KL divergence here is used to compare the policy returned by the model before and after the optimization step. So if you find, for example, the plot of the if you track the plot of the KL divergence and you see that you've got high specs in KL divergence, this is considered usually as a bad sign, because it shows that your policy was pushed too far from your previous policy, which is a bad idea most of the time. And especially as your neural network is a very nonlinear function and in high dimension space, so large changes in the model weights could have a strong influence on the policy. One last thing, but of course not least, there is the value estimate. Since in the policy gradient you're trying to estimate the value of being at this state and following the policy, taking action, and see what will be your cumulative reward. So this should increase during a successful training, and it also should increase as the cumulative reward increases. So these are some of the sanity checks that you should consider for policy gradients. And for example, for key learning strategies, in policy gradient, we measure the exploration using the entropy term. And here, in key learning strategies, we measure that through the epsilon gradient. So finding good epsilon schedules is important, so that you can favor exploration at the beginning, and then you move to taking optimal actions. So this is one important thing. The second thing is to find learning rate schedule that are helpful. So the learning rate should be decreasing over time. And there is another important thing, which is the TD error. This is that this should be decreased over time. The TD error means that our current and this means that our current policy output to the are becoming means that our current policies output are becoming more similar to the true key values that we're trying to predict. And we can see, for example, in the plots, we can see some discontinuities due to the non-continuous evaluation of the target network. But the loss should decrease with respect to single target network updates. So finally, there is the action value estimates. It basically should increase as the cumulative reward increase, same as in policy gradients. So let's suppose that you have done all your you have done your environment. You implemented everything. You choose your baseline. You set up the experimentation pipeline, and you've done the training. And you are quite confident about the behavior of your learned model, and you would like to move on evaluating it. So so here, there's two things that you should consider is that for being able to evaluate your RL agent, you should use a separate test environment. So to be able to evaluate the performance of your agent at any given time. And also, to be able to evaluate it fairly, you should evaluate your agent for n test episode and average the reward you got per episode to have a good estimate of how good your environment is generalizing on environment that it hasn't seen before or not. And and the number of test episodes could range from 5 to 20, and it can be also more than that. So the main conclusion about this presentation is that I try to discuss about briefly about what reinforcement learning is and how make it easier for people to tackle it, especially at the beginning. So one of the main takeaways is that first you should know your environment very well. You should also read about the baseline algorithm. You should know what exists in the literature and how you can use that and take advantage of that. Also, you should also consider, especially, you should consider doing quantitative experiment diagnostics. So, and also you do hyperparameter tuning when it's needed. And one of the important things, of course, after having your model trained, you should evaluate the performance using a separate test environment to see whether you're generalizing or not, and whether the performance is as expected or not. And for better performance, if you are able to do that, it's recommended that you increase the training budget. So I hope that I put here some helpful material that allowed me also to have this presentation and also helped me in my work, which is about the nuts and bolts of deep reinforcement learning by John Cholman, as well as some other materials about deep RL hacks. You can find the links here, and I hope that with all that being said, even if it was a little bit quick and brief, I hope that you've got an idea of how to tackle a reinforcement learning project. I would like to also thank you for joining us. And if you have, I would like to look at if you have any questions in the dialogue chat. Few minutes. Okay, I think there's no question, but of course, we'll be waiting for some other for you if you have any question for some couple of minutes. I hope that it was clear um, because I don't see any questions. If you, I can leave my email address afterward if you would like to discuss some of the topics that I was discussing about and some of the points together. Okay, so let's see, there's a new comment. Okay, so what should I do to begin practicing with reinforcement learning? So here we get back to the slides, I think. So how can I get started? So basically, if you'd like to start with reinforcement learning, you should know about it, and you should check what are the materials that you have access to online. And here I try to highlight the most important ones. Maybe you should start by checking these links. Also, if you would like something that goes into theory and practice in the same time, you should consider having online courses, or also this book that I totally recommend, which is Reinforcement Learning Hands-On, book with tutorials by Maxime Lapin. And after that you try to, if you have a problem that you'd like to solve with reinforcement learning, you can follow the steps that I just discussed about. And if you, for example, if you would like to start experimenting with reinforcement learning and see how this being done, as I said, there's the OpenAI Gym, which offers a toolkit of environments that you can have access to. So there's a lot of things that you can do. You can try environments and try algorithms, baselines, I mean, that exist already in the literature, and try to experiment and see how far you can get with those environments and with the experiments that you will do, trying to tune the baselines and trying to make them work, looking at the TensorBoard plots and trying to analyze the performance. So this way you can get more and more information about the reinforcement learning field before starting doing your custom environment. I hope this answers your question. So what is the minimum knowledge that should I have to begin with reinforcement learning? So basically, you should have minimum knowledge of mathematics, because if you'd like to understand the full details of the algorithms, how they are implemented, and this kind of theoretical details. So you should know about that, and also you should have computer science skills that you'll be able to implement models and doing the best practices, because after all, if you're doing a custom environment, for example, a large part would be about software engineering, because you're going to build the environment, make it efficient, and make it fast, and because that will will highly harm your training time. So building simulator is not that easy. So you should know also about. It's like a combination with mathematics and computer science. Um, And also, if you are very new to the AI field, start by knowing about what is the deep learning, what is supervised learning, how it differs from reinforcement learning, what are the things that you do to be able to, how you do training in supervised learning, how do you make your algorithm really predicts what you're looking for in an accurate way. So. I don't know really what is your background, so these are some of the answers that I've got. Welcome. So, what's the difference between deep reinforcement learning and reinforcement learning? So, the field of reinforcement learning it's not something really new, and it dates back from very early dates. But here, for example, before we had, for example, Q learning, and for example, in Q-learning, you're using tabular Q-learning methods, and here you've got a problem because in Q-learning you're doing the estimate of your action values through a table, so you're limited by the state space. And for example, when playing Atari games, you're having a state space that's really big, and after and you're trying to approximate your state space with you will need to approximate your state space and not using really a tabular learning. And here comes the need for applying deep reinforcement learning as function approximator. And basically, the difference between reinforcement learning and deep reinforcement learning is to use deep neural network to be able to approximate your function and make it work. Hi, Mir. So, great presentation. What are, according to you, the limitation of reinforcement learning? Okay. Mm, so for the So maybe the limitation of reinforcement learning is that is the sometimes the instability of the training. This is to say, for example, sometimes you can see with some algorithm that you can observe during the training a huge drop in performance, and this could be really a limitation because common work right now is trying to make it more stable and more and better. And for example, there's the field of modern model-based reinforcement learning, and there is the model-free reinforcement learning. There was not a lot of work done on the model-based, and this because it was considered is considered as a very hard, and the work is being done on that field. So maybe putting more efforts on that part would be very interesting, and it's what the community of reinforcement learning people are doing. And personally, what I really consider as limitation for reinforcement learning is that, for example, when you have action space, when you work in an environment and you have an action space that is not really fixed, so you've got an action space that changed from one step to another. So not the same action that you have taken in the last step would be the same action that you will be able to take at the next step, and this is considered as a research field that's very difficult, and it's of course it's getting more attention right now, but this is considered as a difficult part. And another thing that that I would like to say is that the limitation maybe is to be able at the end, after having your work done on a simulator, how you will be able to deploy it on real world environments. So this is considered as really tricky, and before doing that, you should really make sure that that you should make sure that your agent will not really make any wrong action, because putting an agent in a real world environment would be very tricky. Um, so I think let's wait if we have another question before we finish the live, because we come to the end of our session. Okay, so I think here we come to the end of our session. Thank you. I really would like to thank you, all of you, for joining us. And of course, if you have any questions, if you would like, after rewatching this session or anything, you can discuss with me, whether on Twitter, or even I can provide my email address. If you have any question also while working on projects, you can get in touch and we can discuss about it. So I hope this was clear for you, and I hope that this was helpful. And please do join us for the upcoming session. And thank you. And please stay safe during this crisis.